Hi, Luyanda. Luyanda,
Good
hi.
day, sir.
How are you?
Hello, sir.
Unjani?
I'm good.
Mm.
Ngiyaphila.
Oh, all right. Okay. Ethi ngisaya ngale studio
Yes,
sizoqhubeka manje ne. Just hang in
yes,
there ngisaya e-studio.
yes, sir.
Yeah.
this now. Okay, quick morning, guys. And welcome. I hope we are all good. I hope we are all good. And it's a very beautiful morning, chilly, and very nice, beautiful weather. Yeah, so as I promised, we're gonna be doing work energy and power today. So that is what we're gonna be doing today. Work energy and power. That is what we're gonna be doing. Can you guys hear me? Did you can you hear me?
Yes, I can hear you.
Okay, great. Good. Very well. Right, let's get started. All right, so we're gonna be doing here this topic. Very simple, but can be a bit tricky, but it's a very simple topic. Work energy and power. One thing that we need to understand first about work energy and power is that we're speaking about the work done by a constant force. That is what we're speaking about. Work done by a constant force. This is what we're speaking about. So when we speak about work, we are looking at the work done by a constant force. It's very important that we flag out that the force must be of constant magnitude. It's very important that we need to flag this one out. So we're looking at work done by a constant force. Hence, our main focus will be primarily on the concept of the force. So you need to be very clear about your Newton's laws of motion if you are to fully understand this topic. Because you are looking at the work done by a constant force. Therefore, we need to know the laws that governs the concept of a force. And those are Newton's laws of motion. By very definition, we say work is equals to these two things. Force multiplied by the displacement and the cosine of an angle between the force and the displacement. Let us emphasize this, that this angle here is the angle between the two vectors, between the force and the displacement. We should reflect it out that this is the force between this. If you guys were already at university, first year doing pure maths, we're going to talk to you about multiplication of the vectors. And this is what we call a scalar product of the two vectors. This is a scalar product of the two vectors, and these are the two vectors. It's a scalar product. Therefore, work is a scalar because this, by very definition, is a scalar product. So work is a scalar, which means it doesn't have a direction. It's a scalar quantity. However, when we speak about work, if we calculate work, there are three possibilities. Work can be positive Work can be zero, work can be negative. But the negative work done does not mean that it's a direction. In this case, it has got to do with the energy transfer. When the work is positive, it means that the force that is doing the work is accelerating the object. Let me repeat this again. When work is positive, it means that the force that is doing the work is accelerating the object. When work is negative, it means that the force that is doing work on the object is slowing down the object. And what determines these things is the angle. It depends on the angle now. So when your angle is between 0 degrees and 90 degrees, then the work done by such a force is going to be positive. I told you guys that you need to know your mathematics or your physics. So this is what we call a domain. So when your angle is within this domain, then the work done by such a force will be positive. But when this angle between the force and the displacement is 90 degrees, then the work done will be zero. And when this angle is bigger than 90 degrees, but less than 80 degrees, then the work done will be negative. I'm going to show you just now also. So we are speaking about the work done by a constant force, which we have said. By the way, when we're speaking about work done, work is done when there is energy transfer. When there is energy transfer, then we say that work is done. Right. Right. So let us look at that. We could be looking at something like this one, which I'm going to show you. We can be looking at an object, a clock, that is being pulled by the force F. So firstly, for work to be done, this object must move. So there has to be a displacement. Otherwise, you are not doing work if this object is not moving. Complicated. So if this object is going to move from this position to that position, such that there is a displacement, it has moved in this displacement, then work is done. But the force must always be active. In this particular instance, this is your displacement, which is horizontal like that. And this is the angle between the force and the displacement. So whenever we calculate work, we have to look at the angle between the force and the displacement. Believe me, if you can figure that out, if you can figure this one out, this angle between the force and the displacement, then you are good. Okay, so that is our concept of work done. And then remember that we said it's a work done by a constant force. So when a force is acting on an object, the object is going to accelerate in the direction of the net force. And remember that from Newton's laws of motion, when we add up all the forces acting on an object, we get a net force, which is given by this formula, mH. We know what's going on.
So I think i-charger yami, phone yami ino-battery.
Angikuzwa mina kuyena. All right, so from Newton's laws of motion, because we are speaking about the work done by a force, it is very important that we flag out that there has to be a net force. So at some point, not at some point, whenever we are doing this, we're gonna be talking about the net force, one way or the other. So look at that. But also remember that we have got this formula from the equation of motion. Vf squared is equal to Vi squared plus 2a delta x, because now the object is accelerating from the initial velocity Vi to a final velocity Vf over a displacement delta x. On this equation 2. Let's just do some maths, some simple maths tricks. Simultaneous equations. Now we want to take this equation 2 and multiply it by the mass of the object. We want to take this equation 2, multiply it by the mass of an object. And when we do so, we're going to get mVf squared, mVi squared, plus 2 ma delta x. We have multiplied equation 2 by m, as you can see. As you can see. And notice that is this mh, which we have said that ma is actually equal to the net force acting on an object. So we are now going to substitute in the place of ma, we are going to substitute F net. And then this is what we're going to get. Let us take this to this side. This is what we end up with. We've transposed this to this side and we've replaced this MA and F net. That is what we've done. But we need to remember that we have said the product of a force and the displacement is actually the work done. In this particular instance, it is the net force. Therefore, the product of these two is actually equals to the work done by the net force. And then when we make that the subject of the formula, we are going to divide both sides by the 2 so that this cancels that. And then what you're going to end up with will be plus mVf squared minus half mVi squared is equals to the work done by the net force. And this is what we call work energy theory. This is what we call work energy theory. But if you look correctly, remember that half mv squared is kinetic energy. So this is the difference or the change in kinetic energy. So your work energy theorem states that the work done by the net force acting on an object is equal to the change in kinetic energy. The work done by the net force acting on an object is equal to the change in the object's kinetic energy. I don't know if there are any questions so far. Any questions so far? So that it becomes a second form. But because we are speaking about the what you call forces, it becomes very important that we categorize these forces as being conservative and non-conservative. Conservative versus the non-conservative forces. So we have to categorize this. When we speak about the conservative force, by the way, a force can be conservative provided there are two things that you need to know. One, the work done by a non-conservative, a conservative force, work done by a conservative force over a previously pair must be zero. Secondly, a conservative force does not depend on the path followed by the object. Conservative force does not depend on the path followed by the object. This is the formal definition that they give to you. I don't know why they do not tell this, because it is very important. It is very important that we have to flag this out, that the work done by a conservative force over a closed path is zero. What do we mean by a closed path? We mean to say an object can move from point A to point B Conservative force does not depend. It matters not how this object moves from this to that. But when we speak about a closed path, so you are going this way. A closed path means the object must then move back from point B back to point A. This is a closed path. For example, I can toss this pen upwards and catch it back to where it started, like that. That's a closed path. You throw something up to the air and catch it back. So that becomes a closed path because you are moving from point A to point B, then back from point B to point A. That is a closed path. So what do we mean by that? We mean to say that if the force that is moving the object from A to B is conservative, then the work done from A to B plus the work done from B to A is zero. That is what they mean. We move from A to B, then back from B to A. If there is a constant force that is moving this object from A to B, then from B back to A, such that when we add the work done by that force from A to B plus the work done by the same force from B to A is zero, then we conclude that such a force is a conservative force. I think let us show you. I think we need to show you this. I think we need to prove that to you, that there is a force that is conservative in a manner that the work done by such a force, the total work done by such a force over a closed path will be zero. So let us look at that. So consider an object of mass m. It could be a marble that is rolled up and inclined. And left. Right. So we have an inclined plane like that. But this is inclined plane. And then you are rolling up a marble, for example. You roll up a marble, it moves from this point A to this point B, and then it will roll back down. Obviously, if you roll a marble up such an incline, it will definitely go back to point A. Definitely. This is just the angle of inclination. That's theta. It's just the angle of inclination. So we are looking at the object as it moves from A to B. And we want to calculate the work done by the gravitational force on this. So firstly, we are looking at the forces that are acting on this object. There is a gravitational force which is vertically downwards. There is also a normal force. which is perpendicular to the incline. So there are these two forces, because we didn't say that it's a rough incline. So we're just looking at this. We are interested in two things: work done by the gravitational force over a closed line. So as the object moves from A to B, we want to calculate the work done by the gravitational force. And remember the formula we've said, the work done by any force is F delta X multiplied by the cosine of the angle between the force and the displacement. Listen carefully. Theta is the angle. This theta here is not the angle of inclination. Look, it is the angle between the force and the displacement. Maybe let us change this so that we can print confusion and call it beta. So that there is a distinction between this angle theta and that angle of inclination. So what are we looking at? The object is moving from A to B. So as the object is moving from A to B, this is the displacement, delta X. And then the angle between the two, this is the angle between the gravitational force and the displacement. That is the angle that we are looking at. Question is, how do I get the magnitude of this angle? And the answer is very simple. So if these two lines are parallel, then this angle here and that angle there are equal. We call them in mathematics corresponding angles. Corresponding angles. So this is your angle beta over there. But you can already see that this is a 90 degrees. So when the object is moving up the incline, the angle there between the force and the displacement will be equal to 90 degrees, which is this one. That's 90 degrees, plus that angle of influence. So the angle between the gravitational force and the displacement is 90 degrees plus the angle of inclination, provided the object is moving up the incline. And what will this give us? We are calculating the work done by the gravitational force. So the work done by the gravitational force in this case, remember, this is mg delta x. We already have said that when this object is moving up the incline, then this will be the angle between the force and the displacement will be 90 degrees plus theta. There is a lot of maths to it. There is a lot of maths to it. But remember that from mathematics, this cosine of 90 plus 100 is actually in the second quadrant, which will be negative sine of theta. Cosine of 90 number theta, beta, negative sine. So therefore, it will follow that this will be the negative from the negative mg delta x sine of the angle of inclination. That is what is going to happen. That is what is going to happen there. So the work done by the gravitational force as the object moves from A to B is that. Now let us look at the very same object now, moving from B back to A, the closed path. Remember the closed path. So we're looking at the very same object. But this time around, our object is rolling down from B back to A. So in displacement this time around is this. Again, we still have the very same forces, gravitational force, which is vertically downwards, and the normal force. This time around, Lindy, we have that end, Cindy. This is the end, this is your gravitational force. So this now becomes our angle between the gravitational force and the displacement. That is the angle. This is still your angle beta. But if you look correctly, this is the triangle, as you can see. Some of the interior angles of a triangle is 90 degrees. So when I add all of these is 180 degrees. When I add all of these three angles, this, that, and this 90 degrees, we are going to get 180 degrees. That is what math tells us. And we can easily prove that. But we are not there. So when we find the magnitude of this, we have 180 minus 90 minus 30. Sorry, we are looking for beta here. Such that angle between the force and the displacement will be 90 degrees minus beta. The angle between the gravitational force and the displacement, when the object is now rolling down, when the object is now moving down the incline, the angle becomes 90 degrees minus beta. Remember that when the object was rolling up the incline, the angle was 90 plus. When you are moving up, it's 90 plus. But when you are moving down the incline, it's 90 minus. Remember this. So notice that. So again, we are looking at the work done by the gravitational force, which by definition, by the very definition, will be this. Gravitational force is mg. The mg is 90 minus 1. And remember again, from your mathematics, that cosine of 90 degrees minus beta is equal to the sine of beta. So this becomes mg delta x sine of beta. And then when we are looking at the total work done by the gravitational force, moving the object from A to B, plus the work done by the very same gravitational force, moving the object from B to A. Remember, let's go back. From A to B, we said it was negative mg delta x sine beta. So this was negative mg delta x sine of beta. And then this is the work done by the same force, moving the object now from B back to A, which is positive mg delta x sine of beta. And as you can see, we are adding the same thing. This and that are the same. But this is negative, that is positive. Therefore, this becomes 0. And what can we conclude? From our definition, remember, from our definition, we have said the work done by a conservative force over a closed path is 0. And we've proven that too. So we can therefore freely and safely conclude that since the work done by the gravitational force over a closed path, A to B, then from B back to A, since it is zero, then we can conclude that this gravitational force is conservative. So the gravitational force is a conservative force. That is what we can conclude because we have proven it to be qualitatively and quantitatively. We've proven it to be that the work done by the gravitational force over a closed path is zero. Hence, we can conclude that the gravitational force is a conservative force. Any questions before we proceed? Any questions? No questions, okay? So we can now say to you that, okay, since we've got these conservative forces, these are non-conservative forces. So we've already mentioned the definition. So obviously the definition will be the opposite of each other. Because one is conservative, the other one is non-conservative. But I want to list the example. Conservative forces will be gravitational force. A gravitational force is a conservative force. We've already proven that. But also, there is what we call, which you guys don't have to worry about. There is what we call elastic forces. Elastic force is like a force of a spring or the elastic belt. Irregular elastic belt. So work done by such by elastic forces are also conservative. But when your main focus is the one, because you guys are not doing your there is what we call technical science. Technical sciences. So since you guys are doing physical sciences, there is a new subject called technical science and technical mathematics. And yep, I was blessed and honored to have been invited to write the textbook of technical sciences. So they do what they call Hooke's law. That is where they speak mostly about elastic forces, but you guys don't have to worry about it. All the other forces, your applied force is non-conservative. Your frictional force is non-conservative. Your normal force, as well as your tension, these forces are non-conservative forces. All of these are non-conservative forces. But because we are speaking about earlier on, we have said there is a work done by the net force. Forces can be conservative and non-conservative. Therefore, when we speak about the work done by a net force, we are actually speaking about the work done by the conservative forces and the non-conservative forces, because they will all be acting on the object. The only conservative force that we have that we're going to be discussing is the gravitational force. And we can tell you now that the work done by this is the same as the work done. See, WC here stands for work done by the conservative force. NC, all the non-conservative forces. So in this case, the conservative force that we're looking at is the gravitational force. And let us mention it to you that the work done when you are lifting an object from the ground to a particular position, then the work done by such a gravitational force will be, it's actually the change, negative, the decrease in potential energy. The decrease in potential energy. How can we prove that? We can easily prove that. Remember, earlier on, we have said to you that this is the displacement, so the object will be moving from here. But this here is the height. And we have already established that the work done by the gravitational force was mg delta x cosine theta when the object is moving down, either up or down in measurement. Okay, let's just look at when the object was moving up, negative mg delta x cosine theta. That is what we have said. But before it was sine. It was sine. But when we look at this by very definition, the sine of this angle theta is opposite over adjacent. This is the opposite side. And this is the hypotenuse side, mathematically speaking. So this would be the height of this incline divided by the hypotenuse, which is delta x, the displacement. Notice that when we multiply both sides by delta x, we end up with the height of such an object. It will follow, therefore, that if I'm looking at this and I see delta x sine theta, delta x sine theta is actually the height of this incline. Therefore, the work done by the gravitational force will be negative mgh. Mg, negative mgh. But remember that mgh is the gravitational potential energy. Therefore, we've proven this that we have said earlier, that the work done by the gravitational force is actually equal to the decrease in gravitational potential energy. Number physics. And when we go back now to saying that, since we have said that the work done by all the forces acting on the object will be this plus that. Remember, earlier on we've said the work done by the net force, we have said that the work done by the net force is equals to, and where was that? Oh, it's here. Work done by the net force, work energy equivalent is equals to a change in kinetic energy. Change in kinetic energy. So we are going to take that to this. Work done by the net force is the change in kinetic energy. Work done by the conservative force, negative change in gravitational potential energy. So that when we solve for work done by all the non-conservative forces, we take this to the right, to the left-hand side, so that this becomes change plus change in kinetic energy plus change in gravitational potential energy. And this is another formula that we're going to be applying. And remember that the kinetic energy is half mv squared. The potential energy is equals to mg h. But if we are to isolate the system so that there are no non-conservative forces acting on an object, if we are to isolate the system, remember, isolated system means there are no external forces acting on such an object. So in an isolated system, what will happen? The work done, because in an isolated system, there are no non-conservative forces. So the work done by the non-conservative forces will be zero. That is an isolated system. There is no frictional force, there is no applied force, there is no tension acting on an object. Then the work done by all the non-conservative forces will be zero, which means what? It will mean that, remember, we've said this, it's changing that, plus the changing that, it will be zero. And this is what we call conservation of mechanical. Only in an isolated system. Mechanical energy will be conserved. And remember that mechanical energy is the sum of the kinetic energy and the gravitational potential energy. That is the mechanical energy. That is the mechanical energy, the sum of the kinetic and the gravitational potential energy. And this, by the way, this is all the theory that you need. This is all the theory that you need in this topic. So if you can understand this theoretically, I promise you that you are standing a very good chance of achieving this. I promise you. That you are standing a very good chance of achieving this. So, at this point, ladies and ladies, we are ready now to look at the questions, because this is all the theory that you need. And actually, even more. Okay. What is this? Okay, find the questions. Is this thing? Okay, now I want us to look now at the previous question papers. See, I think. Okay. And by the way, this is question 5 of your exam. So in your paper 1, we are at question 5 now. Let's look at this question now and then try to make sense out of it. Okay, let's look at this question now. And unpack it. Look at this, okay? The diagram below shows, it's not below. Okay, the diagram below shows a track ABC. The curved section AB is frictionless. Frictionless. From A to B, there is no friction. And guess what? Mechanical energy is going to be conserved. The mere fact that they're telling us that this is frictionless, they are actually telling us that mechanical energy will be conserved. From A to B. That is what they are telling you indirectly. And also, remember that there is no applied force. But from B to C, that is a certain portion. There is, it's a rough surface, the rough horizontal surface or section BC is 8 meters long. An object of mass 10 kg is released from point A. Released, meaning the initial velocity at this point was 0, because you are releasing something. When you release something or when you are dropping something, the initial velocity is 0. You are at a certain height here. The initial height there is 4 meters. Okay? But once you reach this point, at a point B, the final height is now 0. We are at the ground level. The final height is 0. We do not know the velocity. And we are thinking that they are going to ask us to calculate the velocity of an object at B. Okay, they are saying that an object of mass 10 kg is released from point A, which is 4 meters above the ground. It slides down the track and comes to rest at C, and comes to rest at C. The velocity at this point will be 0. That is what they are telling you. State the principle of conservation of mechanical energy in words. I'm going to send you this definition, but okay, let's check from here. You have their exam guidelines. Okay, so whenever you are preparing for this, please keep your examination guidelines next to you, because these are the definitions that we need. Change those, right? Because work, energy, and power. These are the definitions that you need. So these are the definitions that you're going to need. Define work done on an object by a constant force F as F delta X cosine theta, where F is the magnitude of the force, is the magnitude of the distance, and the theta is the angle between the force and the displacement. Okay, and then they wanted us to state the principle of conservation of mechanical energy. There is conservation of energy with non-conservative forces present. Bullet number 3, state the principle of conservation of mechanical energy. The total mechanical energy in an isolated system remains constant. And there is a note. A system is isolated when the net external force, excluding the gravitational force, acting on the system is 0. So that is what they are mentioning to us. So remember, you're getting a principle of conservation of mechanical energy. The total mechanical energy in an isolated system remains constant. That's a definition which we have. So we're not going to write that down. You guys will have to read that. 1.1.2. Is the mechanical energy conserved as the object moves from A to C? No, not from A to C, but only from A to B, not A to C. The answer is a big no. Mechanical energy is not conserved from A to C. It is only conserved from A to B because that is a section that is without the friction. There are no non-conservative forces. But from B to C, there is a non-conservative force because they've said it's a rough surface. There is a frictional force. I don't know if you guys are still with me. Using energy principles only, calculate the magnitude of the frictional force exerted on the object as it moves from B to C. This is a multiple-step object. We need to know what is the velocity of the object at B, because we know what is the velocity of this object at C. How are we going to get that? We are going to use the mere fact that mechanical energy is conserved as the object moves from A to B. So mechanical energy is conserved, which means mechanical energy at A is equal to the mechanical energy at B. But what is a mechanical energy? It is the sum of the kinetic energy and the gravitational potential energy. So kinetic energy at A plus the gravitational potential energy at B must be the same as the kinetic energy plus the mechanical energy is conserved. And we have already mentioned that the object was released. We were told it is an object of 10 kg, an object of mass 10 kilogram. At A, it was released. So therefore, at A, the velocity is 0. We have already listed that. The height at A they have said is 4 meters. We do not know the velocity at B, but we know that the height at B, because you are on the ground, you are at the ground level now, the height is 0. And can you guys please assist us? This is 0, so you don't have to worry about that. That is also 0, you don't have to worry about that. But what is this? Can someone please assist us with that? Cindy, what is the answer there? Cindy, are you there? Yes, what's the answer there? 300. Say that again. I'm going to say. Is it 392?
Yes.
392, yes. This is 5. And then when you divide that by 5, what do you get? Oh, actually, let us also take the square root. Because of that. This cancels that, we've got that. But the square root of 392 over 5. Cindy, what's the answer there?
8,
8 comma
8, 5.
So the object when it reaches the point B, it will be moving with a velocity of 8,85 meters per second. Now, what do they want us to do? We are told that at C, the object will come to rest. It will stop at C. That is what they've said. Comes to rest at a point C. Comes to rest at point C. So the velocity at this point is 0. This is a rough surface. And then how are we going to answer this? We are going to apply the work energy theorem. What does the work energy theorem stipulate? It says the work done by the gravity, the work done by the force is equal to the change in kinetic energy of the object. In this case, the only object as this thing is moving from B to C, it is the frictional force that is doing the work. By very definition of the work, frictional force, this is the only force acting on an object. No, not the only force. The only force doing work. Remember, we've got your gravitational force. Remember, we've got your normal force. And then there is a kinetic frictional force in the opposite direction. Why are we not mentioning these two? The reason why is because the object is moving towards this way, that is the displacement. The angle between the normal force and the displacement is 90. The angle between the gravitational force and this displacement is 90. And the cosine of 90 degrees is 0. So we don't have to mention these two forces because the work done by these two forces is 0. The only force that is doing work on this object is the frictional force, kinetic frictional force. So the work done by the normal force is 0 in this instance. The work done by the gravitational force is also 0 in this instance. Hence, the work done by the net force, the only force that is doing work on this object is the frictional force. Like both. The change in kinetic energy at C, which is the final point, at B, which is our starting point. Notice that between these two, between the frictional force and the displacement, the angle is 180 degrees because frictional force is always opposing the motion of an object. So when we do that, they want us to calculate this kinetic frictional force. The displacement they've set from B to C, they've said it's 8 meters. 8 meters. So our displacement there is 8 meters. The angle between the frictional force and the displacement, we have said is 180 degrees. At a point C, this object is going to stop. We have just calculated that this object at a point B had this velocity, 8.85 at B. And can you please kindly calculate this? Okay, this is 0, we can forget about that. So what is negative that? I think it's going to be 392, negative 392. This will be negative 392. 8 plus 180 will be negative 8. This here. 8 cosine of 180 degrees is negative 1. Therefore, 8 cosine 180 degrees is negative 8. And then we will then divide the both sides by negative 8 to find that the magnitude of the kinetic frictional force will be that. What is the answer? What's the answer, guys? (392) divided by 8, what is the answer? Luanda, what is the answer? Luanda, are you there? Hi guys, what is the answer? Yebosin.
49.
49. And you are done. That's it. That's it. That is it. So this is what you have to do. Firstly, AB is a frictionless surface. Therefore, mechanical energy from A to B is conserved. So we used that to calculate the velocity of an object at B. And secondly, from B to C, we have looked at this object as it was moving from B to C. And when we look at this force acting on this object, the work done by this is 0 because it is perpendicular to the surface. The work done by the gravitational force is also 0 because it is perpendicular to the surface. Cos 90 is 0. Therefore, the only force that is acting, that is doing work on this object, is the kinetic frictional force. Questions? Okay, I'm going to make a glass of water and coming back. Just give me 30 minutes. Any questions before we proceed? Okay, let's look at question 1.2 then. Right, let us look at this. So we must read first and understand what is being said. A motor pulls a crate of mass 300 kilograms with a constant force by means of a light inextensible rope running over a light frictionless pulley as shown below. The coefficient of kinetic friction between the crate and the surface is 0.19. So they are telling you quite a lot of things here. There is a tension force which is pulling this object, because they've said there is a rope. When there is a rope, there is a tension force. Secondly, mass tells you that there is a gravitational force. Mass tells you that there is a gravitational force. And they've told you about the coefficient of kinetic friction. So frictional force is opposing this, but there is also a normal force. There are 4 forces which are acting on this object. There are 4 forces. Question number 1.2.1. Calculate the magnitude of the frictional force acting on an object. Remember that when you are given the coefficient of kinetic friction, then the magnitude of the frictional force is equal to that. In this particular instance, your normal force when the object is on an incline, remember that the gravitational force will have these components. Your gravitational force is got these 2 components. And the magnitude of this and the normal force are equal. So your normal force in this instance will be mg cos theta. Remember that fg perpendicular is equal to mg cos theta, and fg parallel is equal to mg sin theta. Remember these 2 things from grade 11. So in this case, we are given this as 0.19. This is 100. That is 9.8. And the angle of inclination, they said, is 25 degrees, as you can see. What is the answer there? In the way, what's the answer? In the way. Hi guys, don't waste my time, please. Lindiwe, I'm asking you, what is the answer to this? Amsize weseni. Azomulindiwe because I'm cooking you.
500.
Repeat that.
506.
I am Ngozo Sylvia Cat.
506.
And what?
506.
566,
506.
506,
6.
6. I better see how much digits I two after a comma.
26.
There you go. So that's a magnitude of the frictional force for 3 months. We move on to the next. The crate moves up the incline at a constant speed of 0.5 meters per second. Calculate the average power delivered by the motor while pulling the crate up the incline. Okay, before we get to there, remember that power is a rate at which work is done. That's the first formula. That's your average power. The second formula is power is equal to the force multiplied by the velocity. Average velocity, constant average velocity. Excuse me. So these are the two formulas that we need to know. So here is when the object is moving with a constant velocity. So when an object is moving with a constant velocity, this is the formula that we use. How did we get to this formula? We used this definition. Remember that work is equal to force multiplied by the displacement over delta t. And remember that delta x over delta t is the average velocity. So this is how we can write this formula. So in your case now, they want you to calculate the power delivered by the motor while pulling the crate up the incline. So what do we need to do here? We need to find this force that is pulling this object up, because you are already given the constant speed. So the formula that you are going to use is power is equal to force multiplied by the displacement. But we need to find the magnitude of that. It is moving at a constant speed. If the object is moving at a constant speed, when the object is moving at a constant speed, 1, the net force acting on such an object is 0. 2, the work done by the net force is 0. So this is when the velocity of an object is constant. When an object is moving with a constant velocity, then you need to know these two things. When they tell you that the object is moving at a constant speed along a straight line, this is what you need to deduce out of that. The net force acting on such an object is 0. The work done by the net force on such an object is 0. That is what you deduce when you see this word, constant speed or constant velocity. This is what we need to deduce. And then we need to first find the tension which is pulling this object up. How do we do that? We use this. Work done by the net force is 0. So if the work done by the net force is 0, then we go to this diagram. We are looking at these two forces along the direction of the displacement, because this thing is moving this way. So the forces along the direction of motion, there is a tension force, there is a FG parallel. There is also a frictional force. Remember, there is also a frictional force. There are 3 forces: FG parallel, frictional force, and the tension. When we add all of those, they should give us 0. But remember, again, this is a positive direction, that is negative, that is also negative. So the work done by those, that the net force is 0. So which forces are there? There is a tension force, there is FG parallel, and there is a kinetic frictional force. All of which, when we add, they give us a 0. And remember, FG parallel, we have said to you, is mg sine theta. We have already calculated this, so we know. Now let us substitute. This is a 200 kilogram crate. Kinetic frictional force, we have found that the magnitude was 506.26. And if you guys can assist me, Cindy, can you help us here with this? Negative 200 times that, blah, 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 blah. What is the answer of that? Okay, what is that? Negative
1,748. 1,748.
Ngicela uyithape lapha kuma-chat. Can you type it under the chat? Maybe 1,248.76. And therefore, this is the magnitude of the tension force because it is the one that is pulling the object up. So at the end of the day, we're going to end up with the power delivered by the motor. When the object is moving at a constant velocity, this is the formula that we're going to have to use. And this velocity, what was the velocity? 0, they set this object to with the constant velocity of 0.5 meters per second. So what do we get when we divide there? Let me check this. 8, 7, 4,38. Power is measured in watts. Am I correct?
Yes.
And that's it. So that is how we're going to be doing this. That is how we're going to be doing this. So, like I've said, as you can see, well, if you want to understand this topic, you need to revise your Newton's laws of motion, firstly, because we are speaking about the work done by a constant force. So we need to revise the Newton's laws of motion. When we do these things, you definitely going to need to do that. As you have seen, we went back to looking at the free body diagrams. So we had to draw these forces acting on an object. You definitely going to have to do that whenever you're looking at this. You need a free body diagram, whether they've asked you or not, but you definitely going to need to draw a free body diagram. And you need to read and understand, read to understand before you answer the question. I don't understand why would people bother themselves trying to answer a question that they don't understand. Firstly, first things first, study the question. Understand what the question says. The motivational speakers, they will say to you, spend 80% of your time, if you want to chop down the tree, spend 80% of your time trying to sharpen the axe. Most of your time should be spent on sharpening the axe. Then 20% chopping down the tree. Same thing applies here. 80% of your time should be understanding the question. Then 20% answering the question. Because if you understand what you are reading, then the chances are very good that you are going to be able to correctly answer the question. We are sick and tired of people who are busy trying to answer questions that you do not understand, trying to solve a problem that you do not understand. Look at where we are as a country. Load shedding. People are busy trying to solve a problem that they don't understand, and they end up creating even more problems. We are tired of such people. We need people who understand, who read, who study to understand. Otherwise, we're going to end up in more mess. We find ourselves in a very bad position going forward. And you guys are the future of this country. We need you to be different. We need you guys to be different. You are the future. Young people are the future of our country. So we believe in you. That is why we are teaching you. So that you can be better, so that you can make this world a better place. We are meeting again tomorrow. Tomorrow we meet at 9. And our boss from Sasol is going to be coming around. She will just pop in and then leave. We just want to see what we are doing with you. So if you guys think that this is for free, no, it's not for free. It's very expensive. So you guys are sponsored by Sasol and Komatu. Komatu, usually. I'm not sure if you guys can see from the camera. Can try to rotate this camera so that you will see. Okay, I think you guys can see. So there is Sasol emblem. There is Osizweni. We are Osizweni Science Center. And then there is Komatu Joy. If you can see from the screen. These are the people who make this possible for you. It's very expensive otherwise. It's a very expensive program if you ask me. So they are the ones who are giving us money to assist you guys. So one of our, someone from Sasol is going to be coming tomorrow. So at 9, we meet and they will just hop in. Hey, what is going on? They will just come and hop in just to see what we are doing here. So we are meeting tomorrow at exactly 9 o'clock. Yep. And by the way, the boss at Sasol, generally is Charlotte Mukwena. If you guys know Charlotte Mukwena, Bonang Mateba's mom, Mama Waga Bonang Mateba. She's our boss at Sasol. We report to her. She's the one who approves everything that we do here. She's the one who gives us the money, the budget, and everything. Guys must really make sure that we do not waste Sasol's money, that we do not waste our time and energy on you. Okay, we are done, guys. Let us meet tomorrow at 9 o'clock. I'm not sure if Mr. Maka will be available for me. Let me call him. Looks like he's out of the office, so this matter is not around. I'm not sure about next, but possibly tomorrow we're gonna have a main session tomorrow. And we are done by 6:20 a.m. Let's meet tomorrow. Luyanda. Oh, no, please. Thank you.